So here we're going to study parametric surfaces. Now, we've already studied parametric curves quite a bit in this chapter, where we are looking at things of this form, right? A vector function that's a function of the parameter t is given by this vector equation where we have these different functions that tell us what the x, y, and z components should be. Now, a picture that I think is helpful, especially to understand surfaces, is that what we're doing here is we're taking just a simple number line that represents t. Let's just say this number line here represents t. Then what we're doing is then we are mapping these values of t onto some curve that's being formed. So, maybe there's our curve. So the idea here is that for various values of t, those go along with specific locations on the curve. So we're kind of going from our domain, that's this number line, to this curve that we're forming. So with parametric surfaces, you're going to need more than just a number line in order to create this curve, create this surface. You're going to need a region in a two-dimensional space, right? So here, instead of just using a t, we're going to use a u and a v axis. And then we're going to form a domain within that uv plane. But the idea is the same as with the curve that I drew up here. So the idea is we take a particular uv and then we map it to a spot on the surface, all right? And specifically, we're mapping it to a vector, right? But still, the point is this point is associated with this point on the surface. Kind of a nice visual, I think, to keep in your mind is that if I lay out a piece of tin foil flat on a surface and I cut it out in some shape, then I could take that piece of tin foil and put it in three-dimensional space, and mold it and give it some height and have it turn into a surface that's shaped more like this one. For some reason, that mental image kind of helps me understand exactly what's going on here. All right, so let's start with a really simple object, a plane. And so we know that if I was to ask us to graph this just using technology, what we would do is we would get the z all by itself. So we have z is equal to 2 minus 3x plus 2y. So I get the z by itself. And then I could go to some sort of grapher that allows you to graph functions of x and y. And then I would just type in that formula. So z equals 2 minus 3x plus 2y. So there's my sphere. Okay, so how do I do this as a parametrically defined surface? Well, the idea here is I just need to give it a formula for the x, the y, and the z component. But we already seem to have a pretty good formula for z here. So what we can do is we can say, let's let the x just be equal to u and the y be equal to v. And if we do, then what we can say is that the x component is just u, the y component is just v, and then the z component is 2 minus 3u plus 2v. All right? So you might say this is kind of trivial. Why are we even bothering with this? Well, there's going to be situations where it's not just as simple as letting x be u and y be v, but this is kind of doing the simplest case so that we can understand what comes later. But let's just double check that this makes sense. If I go into the grapher, I can also click this, surface, and you can see it's defined as a vector function of u and v. So I'm just going to type u in for the x, v in for the y, and then 2 minus 3u plus 2v. And of course, we better get the exact same plane. And of course we do. All right, so let's look at one that's a little bit more tricky. It wants us to identify what this curve or this surface is, and then go ahead and sketch it. So when I'm looking at this, I see a cosine in the x component and I see a sine in the y component. One of the things that we want to watch out for is if we're trying to figure out what type of surface a particular equation makes, and we see cosines and sines, then it's very likely that we want to be trying to make some sort of trig identity show up. And our favorite trig identity, of course, is cosine squared plus sine squared. So what I suggest we do here is I can see that if I square the x and I square the y, I'm going to get that Pythagorean identity showing up. So what I'm going to begin with here is I'm going to say x squared plus y squared. So I'm starting off with a statement about x and y because that's, traditionally the way that we've looked at surfaces. But according to this formula, right, we know that this is the x and this is the y. We can rewrite this in terms of u's and v's. Just like this. Okay, and then let's see what we can do to simplify this. So this is going to be v cosine squared u and v sine squared u. But then that's going to allow me to factor a v out. And so see what I've been able to do here is I've been able to take x squared plus y squared, write it in terms of the formulas based on the parameters u and v, and I'm trying to now make z show up. So if I can make z show up, then I've got an equation that involves x, y, and z. And of course, I can see that v is my z, and this is 1. So that, of course, is z. So what that tells me is that this is really just the surface described by z equals x squared plus y squared, right? But we know what that is, right? That's a paraboloid. And so, and remember, if you're kind of not remembering exactly what it looks like, you sketch traces. So I could go and 1, 2, 3, 4. Do a few tick marks in each direction. So what I can do here is go ahead and sketch traces. So in the YZ plane, it's just z equals x squared. So that's going to be here, 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 there, and there. So we've got a parabola there. And then in the XZ plane, z equals y squared. So same idea. Right there. And then, of course, we can connect all that up with the circle on top. Even though it doesn't really stop there, that kind of gives us a good idea of what that looks like. I'm going to clean this up here. There we go. All right, so we got ourselves our paraboloid. And then we can always use technology to make sure we're on the right track here. So if I get rid of this, and then I change these formulas to the square root of v times the cosine of u, and the square root of v times the sine of u, and then v, and then of course I get that paraboloid. And to give us a little bit better of a view of this, increase that discretization, and now you can really see that paraboloid really well. All right, so in example 3, it says write the rectangular equation for the surface with the vector equation given and observe the graph using technology. I put a graph here in the notes. We can ignore it though because this is going to be a pretty tricky one to sketch. So we're just going to go ahead and write out the rectangular coordinates version and then use technology to get a look at this thing. All right, so if you take a little time to observe these x and y components and the z components, you might look at these for a while and say, okay, how do x, y, and z relate? If you look at the s's, you have an s here and an s squared here, and then in z you have s cubed. The x has a t squared, the y has a t, and z has t cubed. So what it looks like is that if I take x times y, well, that's going to give me s times t squared, and multiplied by s squared times t, which will give me s cubed times t cubed, which gives me z. So what this tells me is that this is z is equal to x times y. But we now have two ways that we can express it. So on the one hand, we can go ahead and type in z equals x times y. It's kind of a cool function, right? But if I wanted to do this as a surface, then I could do exactly the formula they gave us. So we're going to have to do, instead of s and t, this calculator here only uses u and v. So u can be our s, v can be our t. So I'll say u v squared. I'll say u squared v, and then u cubed v cubed. Okay. Now this is pretty interesting. You'll notice that the shape of this thing or the way this thing looks changes a whole lot. And you might say, where did our other graph go? Well, what I want you to first look at is look at the scale here. The z is going from negative 15,000 to 15,000. So the x's and y's from negative 100 to 100. This is a completely different scale than what we were seeing up here. Okay, but understand it's very different to say that x goes between negative 5 and 5, and to say that u goes between negative 5 and 5. Right? You're going to get much larger values when you let u and v range in that region. Also, all this empty space here, the reason for that is because you're limiting u and v. Okay, let me go back to our very first page for a second. So what we're doing is we're limiting u and v, what it can be here, and what's happening is when we limit the u and v over here the way we are, it is only mapping those points to a certain part of the surface that we've created. So the answer to what's happening in these gaps is it's not that there's nothing there, it's just that the u and v points that would map to these spots in these white areas are outside of this little box in the UV plane that we've created. So this is the same graph, right? Just take a mental image of this for a moment. This is the same graph as this. It's just that in the graph we were just looking at, a lot of these things here, like values right in here, are just not in that negative 5 to 5 UV range. Okay, and so we're not seeing them. All right, so let's look at another example here. It says find the parameterization for the bottom half of this ellipsoid here. Okay, and so first of all, what I want to do actually is give you two ways that we could parameterize this. Okay, one way is just drawing inspiration from our very first problem. So if when looking at a formula you feel like you could get one of the variables by itself, then it's fair just to let the other two variables be u and v, and then solve for, in this case, the z. So if you feel like you can do that, then that's always a fair way to do it. So in this instance, because I'm only looking for the bottom half, I can isolate z. So I'm going to do that. So I'm going to first say that z squared is equal to 1 minus x squared over 4 minus y squared over 4. Now, because that we only want the bottom half of the ellipsoid, I can go ahead and take the square root of both sides and then only pick the bottom one. So I'd say z is equal to the negative square root of all this. So I was able to isolate one of my variables, so that means I can let x equal u and y equal v. And so then my parametrically defined surface can just simply be u, v, negative square root of 1 minus u squared over 4 minus v squared over 4. All right. And we can go ahead and go check to make sure that this in fact does give us the bottom half of an ellipsoid. So I can say u, v, and then it's negative square root of 1 minus x squared over 4. Sorry, 1 minus u squared over 4, excuse me, minus v squared over 4. All right, and that's just kind of grainy because we need our discretization to be a little better, so we're going to go like that. Okay, and there's the picture we get. Remember that the steeper you get here, the more trouble it can have graphing these little areas here. So don't be alarmed by that. But definitely have the bottom half of some sort of ellipsoid here. And this one, in fact, notice that the C scale here. So if you wanted to get a representation where z is on the same scale as x and y, remember what you can do is just go to fixed bounds, and then you're on more of a level playing field. And what I might choose to do here is change these so that I could see a little bit better. Okay, that would help me see the bottom half of that ellipsoid just a little bit better. All right, so now let's go and talk about a different way we might do this. So one of the things that we studied at the very end of chapter 9 is we studied the idea of using polar coordinates, cylindrical coordinates, things like that. Okay. So the question then becomes, if I take this formula that I have, I'll put a dividing line here, could I use something like polar coordinates to help me parameterize this? So in other words, here's what I want to shoot for. I want to first of all, let x equal r cosine theta, and let y equal r sine theta. So if I do that, then in here, I can recognize that if I let x equal r cosine theta, y equal r sine theta, then this x squared plus y squared, if I put those together as a first step, yes, I could plug these both in, but remember, if you're working in polar coordinates, that x squared plus y squared always equals r squared. So this becomes r squared over 4 plus z squared is equal to 1. So I can subtract that from both sides. So I get z squared is equal to 1 minus r squared over 4. So then z, just like in our last one, we're going to take the square root of both sides, and because I want the bottom half of the ellipsoid, z should be negative. And I get this. So what this allows me to do is to write a parametrically defined surface where, first of all, we're going to say r, and in our grapher, we're supposed to use u and v, right? So what we'll do is we'll let r equal u and theta equal v. So what's going to happen here is we're going to have, for the x, u cosine of v, u sine of v for the y, and then for the z, it'll be this formula we came up with here, negative square root of 1 minus u squared over 4. So there's an alternative parameterization of this surface. So let's go punch that in and see what we get. So we'll have u cosine v. Oops, something happened to my u there. We'll have u sine v, and then the negative square root of 1 minus u squared over 4. And the interesting thing about this one is that I get a much nicer picture, right? In fact, let's get rid of this here. We get a much nicer picture out of this because of the nature of how x, y, and z are being determined. And it kind of makes sense because, you know, this is the bottom half of this ellipsoid here is, you know, it's not a, I guess I would say it this way. You know, it's an ellipsoid, so it's not a sphere, but there's a lot of circularness to it. And the idea of polar coordinates is that it does things like circles, you know, a lot cleaner. And so it has a much easier time actually making this graph than when I was kind of trying to build a parametrically defined surface off of rectangular coordinates. All right, so let's look at example 5. It says, find the parameterization for the portion of the cylinder, x squared plus y squared equals 9, in the first octant for z going from 0 to 3. Now, a good general principle here is that if they're telling you that a particular variable is going between 0 and 3, then a lot of times that means that we want that to be one of our variables, right? So never lose track of the fact that you're trying to build something like this. So you've got to find two parameter values that can generate your x, y, and z components. So I'm going to go ahead and say that z should be one of the parameter values. And since it's the first one I'm listing, I'll list it as u. Okay. So what about our other one? So let's think about what varies and what changes. Okay. We're on a cylinder here. So that should make us think of cylindrical coordinates. And in cylindrical coordinates, remember, I'll just make a little note over here. Cylindrical coordinates, we have three different values. Here we have r, theta, and z. Well, z is already spoken for. We've used that one, but we can't use all three. So if we look at r and we look at theta, we have to ask ourselves which one is staying the same and which one is changing. Well, because we're on a cylinder, right, x squared plus y squared equals 9, that's r squared, right? So we know that r is equal to 3 at all times. So that means that the r is never changing. So However, theta is changing, right? So that means that theta should be our other parameter value. So my u is my z and theta is my v. So the x values on this cylinder are 3 cosine v, 3 sine v, right? This is just coming from r cosine theta, r sine theta. And then, of course, the z is free to be whatever it wants. So we just put a z right there. Now, in order to create this thing, right, remember what we're looking for here. We're looking for this, for z to go between 0 and 3. But then we're also looking for the circle x squared plus y squared equals 9, which is a circle of radius 3. So I've got to do that. But then I'm going to go up like this as well. And draw that part of the cylinder that's only in the first octant that goes between, the z values go between 0 and 3. So we've got to specify that. So you can see here, I'll have to apologize here. I should have put u, right? Because I said z equals u and theta equals v. So here, this should be a u. But that actually brings up a good point. There is absolutely nothing wrong with using the actual letters. So if I wanted to, what I could have said was r as a function of z and theta is equal to 3 cosine theta, 3 sine theta, z. That would be totally fine. I've just kind of gotten in a habit of saying u equals one thing and v equals another because that's how we're going to punch it in into our technology. But it's totally fine to just keep it just like this. So we've got our picture there. But what we do have to do is we also have to state the limitations on these variables. So we know, let's start with the one on the bottom actually. We know that if you're in the first octant, theta has to always be between 0 and pi over 2. And z is always between 0 and 3 based on the instructions. And then up here we'd have to say the same thing. So v is between 0 and pi over 2. And u is between 0 and 3. And so if I go back to our grapher here, then I can type this in. So it'll be 3 cosine v, 3 sine v, and u. And of course here what I get is the full cylinder, right? So I got to put my restrictions on. So u is only allowed to go from 0 to 3. And then v is only allowed to go from 0 to pi over 2. And there's where I get my quarter of the cylinder here instead of the whole thing. All right, so one last example. This one wants us to find the parameterization for the cap of the sphere x squared plus y squared plus z squared equals 16. So when they say the word sphere, kind of like in the last one, we had a cylinder. We thought about cylindrical coordinates. Here I think we should think about spherical coordinates. So we know that that's rho, theta, and phi. Now we're only going to be allowed to use 2 of these, right? So what we have to think about is what is changing and what's not changing. Well, because we are on the cap of a sphere, because they're telling us x squared plus y squared plus z squared is equal to 16, that actually tells us the variable that's staying put. right? We know that means rho squared equals 16, so rho is equal to 4. So rho is frozen. So we do not need that to be one of our variables for our parametrically defined surface. All right, so now let's list out what x, y, and z are. Okay, so for spherical coordinates, remember, x equals rho sine phi sine, cosine theta. Y equals rho sine phi sine theta. And then z is equal to rho cosine phi. So at this point, I can list out x equals, instead of rho, I can say 4 sine phi cosine theta. Y equals 4 sine phi sine theta. And z is going to equal to 4 cosine phi. So it looks like what's happening here is that theta and phi should be our variables. And so that's what we'll do. And literally what I just wrote out there, based upon our formulas for spherical coordinates, is exactly what I'm going to write out here. So I'm going to say 4 sine phi cosine theta, 4 sine phi sine theta, 4 cosine phi. Now the hard part of this problem is going to be to decide what theta and phi should be. So remember, theta is the angle made in the xy plane. Phi is made starting from the positive z-axis and measured this way. So you can imagine that if I have just the cap of a sphere, it's saying that the z value should go between 4 over root 2 and 4. So if I go up 1, 2, 3, 4, the idea here is we only want the cap of the sphere. So we only want something like that, right? And so then the question becomes, okay, how far down is it that I'm wanting to go? So I'm not sure what that is yet, but I'm going to sketch a picture here. The idea here is if we're going to create just the cap of a sphere, I need to know how far down here I need to go. Okay? And I can make this fairly accurate. If I take 4 divided by the square root of 2, that gives me about 2.82. So I actually drew this really nicely. 4 over root 2 is approximately 2.82. So this is a really good picture actually on accident. So that's about where 2.82 is on the z. So the idea here is phi goes from the positive z-axis to here. So I can let phi be all these values from 0. There's no question we can start at 0 because theta or phi equals 0 is here, all the way down to whatever angle this makes. So let's think about what that would be. So one thing that we can always do is try to figure out what phi is when z is equal to 4 over root 2. So the key then is just going to our z formula. So if z equals 4 over root 2, what is phi? So multiply by both sides by a fourth. So I get 1 over the square root of 2 is equal to cosine of phi. But let's think about this. On the unit circle, when is the cosine equal to 1 over root 2? Well, that happens when phi is equal to pi over 4. So when this thing hits pi over 4, that's when the z value for the sphere is going to be at 1 over root 2. Or excuse me, 4 over root 2. So that means we're going to let phi range between 0 and pi over 4. Now theta, of course, that can be anything. That's no big deal because theta is the angle made in the xy plane. So we want the whole thing, right? We want this thing to spin all the way around to create the cap of the sphere. All right, so this is a perfectly great answer. Now the only thing I'm going to do before we move to the to use technology to make sure we're doing this right is I'm going to just change the names of things. That's all, right? So we're going to make one of them u, make one of them v. So I'll let theta be u, and I'll let v be phi. So this will be r of uv is equal to 4 sine v cosine u, 4 sine v sine u, and then 4 cosine v. And again, u can go between 0 and 2 pi, and v can go between 0 and pi over 4. So when we put that into our graphing technology, hopefully we do end up with the cap of the sphere. So let's see here. So 4 will go sine v cosine u, 4 sine v sine u, and then 4 cosine v. All right, so first we'll fix that discretization, make that a little more refined. And then we're going to let u go between 0 and 2 pi. And we're going to let v go between 0 but only pi over 4. Now at first you might think a big mistake has been made. But we've had this happen to us before where they changed the z on us, the z scale, so that it becomes very different than x and y. And so, of course, that makes something that is a sphere look not like a sphere anymore. So this would be a good one to go to the bounds and make them fixed so that they're all the same. And now this is much better, right? Now I can definitely see that this is, in fact, the cap of a sphere because now I got my x, y, and z's all using the same scales. And you can kind of see I'm sitting up out of the range here. I can still see it fine, but maybe you change your x, -4 to 4, -4 to 4, because the radius of this sphere is 4, right? And then my z probably should be something like -4 to 4 also. And now it's actually, you can see where the sphere would have fit in this box, and we're only getting the cap of it